I'm greatly honored to introduce the 2023 Pioneering Clay Science Award recipient, Dr. Sue Brantley. Sue is the Evan Pugh University professor and the Hubert and Mary Barnes Professor of Geosciences at Penn State University. For a long time, she was the Earth and Environmental Science System Science Institute director, at least when I was there, for sure she was. And her research has focused a lot on how water interacts with rock, how rock becomes soil, and more recently in how the environmental impacts of hydraulic fracturing from the oil and gas industry. In addition to all of that, in 2012, President Barack Obama named her as a member of the Nuclear Waste Technical Review Board, and she has published more than 300 peer-reviewed journal articles. She's a member of the U.S. Academy of Sciences. She is a foreign member of the French Academy of Sciences. And if I say on a personal note, she is one of the greatest teachers and mentors that I've had the pleasure to be around. Even when I wasn't, technically her student when I was at Penn State, she still found time to mentor me and take care, as she's done with all of her students who passed through her many NSF-funded centers and initiatives. So without any further ado, I'm going to present Dr. Sue Brantley, who's going to talk about discovering the clay reactions beneath our feet. Dr. Brantley.
I have to say, when you get introduced, the things that mean the most as you get older are things like when an ex-student tells you how much you meant to them. So I really appreciate that. So I'm happy to talk today about some work that we've been doing at Penn State. And the co-authors here really should be the people presenting this. Let me see if I can get myself organized here. And they're shown here, Ruishu Liao and Jinggu. Jinggu is now at Oak Ridge National Lab. Ruishu is at Lanzhou University. And I also took this chance to put up the title page of their paper so that you can go to it and get all the details if you like. And also, I can't remember why, but this was my original title and I didn't go with it, but I kind of like this one too. So I got to use two title slides in this way. So just as Randy talked about the trajectory of his career, in my career, I kind of started small. I was a chemistry major as an undergraduate, and I liked to do controlled chemical experiments in the laboratory. But as I went along and I started realizing that I couldn't extrapolate what I was measuring in the laboratory to the field, I started moving into the field and working on larger and larger systems. And so that's what I find most intriguing today is how can you use the beautiful things that all of us and all of you do in the laboratory and actually make quantitative predictions in the field. What we're trying to do in this particular work is go from the very small scale, the kind of scales that Randy talked about, up to, what does it look like when you have weathering of a class size hand specimen, up to a soil profile, and then to watersheds. And to me, this is, what's really exciting is, what is the distribution of weathering in 3D beneath our feet? And I would just pose to you that we really don't know for, a lot of reasons. And I put this quote up here from Marty Frisbee. Other people have said this also. In many ways, if we can take a sample and bring it into the lab, we can understand a lot about that sample. We can measure all sorts of things about it. But as soon as you get to the size range, certainly of soil profiles and watersheds, we lose that ability to measure so many different things, especially as geochemists. And so in many ways, this is the scale we don't understand, and this is where all our problems are as a society. So that is sort of a subtext to what I'm going to talk about. So why is weathering important? Well, there's a lot of different reasons. One is it makes clays and all the beautiful clays that you all know a lot more about than I do. But another reason is that weathering creates and changes porosity in the subsurface. And certainly our water resources, our groundwater resources, are stored in porosity in the subsurface. And the movement of water is dictated by permeability in the subsurface. And we don't really know that much about the distribution of porosity and permeability in the subsurface, but we model it with our water resources models. And this is just from a paper by Banks et al., where they were pointing out that in A, we don't know what is beneath our feet, so maybe we just assume it's homogeneous. And if you all know any homogeneous rocks, let me know about them. B, maybe they go and they make one layer that's more or less homogeneous, and then beneath that, an impermeable boundary, which is also not common. Or maybe there's two different layers. And I don't think any of these capture what's really going on. And so sort of a subtext of what I'm going to talk about is how weathering, as water hits the rocks at the surface, is going to change the subsurface. It's going to dictate where that water can go to some extent. So I think of this weathering in the subsurface almost like a landscape beneath us. And that's the picture that I'd like you to take home from this, is that, there's a landscape that we see with our eyes, but in the subsurface is a landscape of weathering reactions, many of which are clay reactions. We don't know what those landscapes look like, but we would like to. And so can we learn to predict those kinds of landscapes? Okay, all that beautiful landscape imagery. Now I'm going to go to 1D. I'm going to do what I'm telling you is not so great, the reductionist, but you start with what you can understand. So let's think about this in a 1D system. Well, nothing is really 1D, of course, in the natural systems, but if you want to think of weathering into some kind of rock, well, you start simple. I would think, I asked this of Randy yesterday, I would think one reason he started with forsterite was that it's simple. He said it was funding, but I bet it was also because it was simple. We're going to start weathering a rock that only has, one lithology in it. It's going to be shale is what I'm going to talk about here. And we're going to go to a ridge because if there's anything close to 1D in terms of weathering, water comes in and, more or less goes through in a 1D kind of direction. And at the same time, rock is being pushed up from below. So it's kind of a 1D system. So we'll go to a ridge and hope we can try to understand it. So there's the rock coming up from below. And this always confuses people because I'm not necessarily talking about uplift. If I'm standing at the top of a ridge and if erosion is removing soil beneath my feet, and if I can be geologically old, if you'll let me be, I am old, but I'm not geologically old. If you let me be geologically old, if I can stand there long enough, as that soil is being removed from my feet, I'm still standing on something. So material is actually coming up from below if you take that sort of opposite perspective, okay? And that is indeed how geologists, how we think about this. And so water is going, I gotta remember which hand to use and which button to press. So water is going down and then the rock material is coming up, if you think of it from that perspective. It's moving up over very long geological timeframes. So the water is the most important reactant, but the two other most important reactants are oxidants like oxygen, and then acid generating reactants like CO2. So that moves down, solubilizing and oxidizing whatever's in the rock. And you can see two kinds of reactions that I'm talking about. I'm not saying that MgO is out there. I'm saying that's the component. So the base metal cation oxides are pretty much reacted with the acid promoted reactions. So at the same time, I mean, that's sort of obvious. You probably thought about that before. But at the same time, as bedrock comes up from below, it starts fracturing because you're removing a rock from above it. And so the stress release allows fractures to open. Those blocks that are subtended by the fractures then move up really slowly through that weathered material, which I call regolith. And as it moves up, they get smaller either from further fracturing or from dissolution. And so we have been trying in our group to put together all those different kinds of processes to understand weathering. So solubilization, and then even looking at particle size and how particle sizes change as a function of depth in this weathering paradigm. So very often the way I think about regolith on a given system is I think about it as if it's an ideal steady state. And I've even written a paper with Marina Lebdeva where we argued that this ideal hill ideal or ideal steady state, it's kind of like an ideal gas. It never really happens, but it's a helpful way of thinking about the system. And that is namely that if you have old soil or regolith anywhere, and if it's lasted for a very long amount of time, then at some level, the rate of erosion at the surface has to equal the rate of that weathering advance so that the weathered material can stay more or less constant or at a constant steady state. So why would that happen? Well, many of us think it's because there's feedbacks between erosion at the surface and the weathering advance. So this is just the conceptual view of how I think of weathering at the ridge. So we've modeled this with reactive transport models. I'm not going to show you any of the equations. It's going to jump to what the, what the output is. And hopefully you can start thinking about this so that when I start showing you lots of data from our field site, that will make a lot of sense to you. So we're going to do reactive transport. We're going to put water at the top, and we're either going to advect water through it, or we could have solute transport by diffusion. And the rock, we're going to say, is just quartz plus albite, and it's going to weather to quartz plus kaolinite. Again, we're making this very, very simple. And we always normalize the albite concentration. Albite is feldspar. It's a reactive feldspar. Quartz is, in this model, is non-reactive. So we always normalize the albite, and it's not really important how you do this. It's very important when you do it for soils, because so many different minerals can be dissolving at the same time. In this particular case, it wouldn't really matter, but I use this variable called tau, which is the mass transfer coefficient. Suffice it to say is that it's a way of using the insoluble component quartz with the soluble component albite, so that 0 means you have the same amount of albite or reactive material as the parent, as the original rock, and -1 means it's 100% depleted. So I'm going to use tau throughout this. I'm going to use it for different components, but all you really have to remember is that 0 means parent composition, -1 is 100% depleted. Okay, so this rock came to the surface and it plotted right there along 0, so it was parent composition everywhere. And then as the albite was removed, if solute transport is by diffusion only, you get what we call a reaction front. And this is with time. So this is short time to long time. Each of these curves is a time, calculated from the reactive transport model. And what this means is that at the surface, at the very surface where you can stand, this is about 75% depleted with respect to the reactive mineral, 75% of albite. And so this is the reaction front. That's the only place where the reaction is happening. Eventually, with time, it goes to 100% depleted, and then you get a complete reaction front shown here, and then it moves down. That's that weathering advance I was talking about. So if we add, so that is a reaction front. That's the only place in the rock where the reaction is happening. And it moves down with time in this case, because I have no erosion. I haven't put erosion in. This is the reaction front, and I would just like to suggest to you, you can see these everywhere around you. Every time you see a road outcrop of a soil profile, go look at the reaction front, because it's cool. It's telling you a lot about what's going on geochemically. And that reaction front is wider, typically, if you add advection. So in this case, the solute transport through the reaction front was only by diffusion. Now we've got advection. Here's that weathering advance with time. It's faster with the advection, and the reaction front is wider. And this width of this reaction front is really dictated by the Damkohler number, which is the transport rate, so how much advection of water through the system divided by the reaction rate. So if you have a really fast reaction, your reaction front will be really narrow. This is fast compared to the transport rate. And if you have a slow reaction, you'll have a wide front. And that's going to explain everything I tell you the rest of the talk. So just sort of try to hold on to that. Okay, now, not only is there a reaction front, but there's also the depth of that front. And that is basically dictated by the velocity of the water going through times the solubility of the mineral divided by how much was there. Okay, so there's two things, the reaction front thickness, and then how deep the regolith is, how deep that front has gone into the surface. Okay, but I did say that in most cases there's erosion, in many cases there's erosion. And so we can run the model so that that weathering advance rate is equal to the erosion rate, in which case you get a steady state thickness. And that's what we have down here. And you still have reaction fronts, but if you have a very slow erosion rate, you can have a buried reaction front that's very narrow, like this one here. But if you have a very fast erosion rate, well, your albite can make it all the way to the surface. So if you go to the top of a mountain that is eroding very fast, you'll see feldspar underneath your feet. If you go to most places in Pennsylvania, you won't. And that's telling you something about, the rate of transport, of fluid transport, the rate of the reaction, and then the rate of erosion. Okay, so now you know pretty much everything you need to know. And you can go back to sleep if you're like me. I have periods of awakeness and periods where I'm not so woke. And the only other thing I can tell you is that this fraction here of albite that comes to actually to the land surface, which in this case is like 0.5, that tells you the fraction of loss of mass by chemical weathering divided by the total loss. So chemical weathering plus the erosion rate. So in this case, for this simulation here, 50% of the albite was lost to chemical weathering. In this case, in this slow erosion case, 100% of the albite was lost to weathering. So this is called by some people the chemical depletion fraction. And way at the end of the talk, it's going to come back. So we'll see if you retain it. Okay, so let's go to the field. Let's talk about some real minerals that are, or rocks that are weathering. I'm going to take you to a shale, because this is the Clay Mineral Society. This is in Pennsylvania, which is up here. If you don't know where Pennsylvania is, it's right in central Pennsylvania, Penn State. And a little tiny watershed, 0.08 square kilometers on shale. Why is it so small? Well, partly shale erodes so easily that the watersheds on shale tend to be very, very small. So this is the ridge around here. Here's the valley. Here's the outlet. We have many boreholes where we've looked at the distribution of the minerals as a function of depth. And I'm going to start 1D with some different boreholes, and I'm going to try to help you put it into context in 3D. This is a Silurian age shale, humid, temperate climate, slow eroding, something like 25 meters per million years. So we're going to start at the northern ridge. This is the borehole furthest from the outlet that I'm going to show you. And the first reaction we see in these shales is pyrite oxidation. So we know this is happening because we see pyrite framboids, 10 micron scale bar. And at depth, this is a tau plot. So this is pyrite is present at the concentration in the original rock. Here's the reaction front. And then there's no pyrite left. Well, how do we know that this is a reaction front and not just a stratigraphic change? Well, up here, when we look at the rocks, we still see framboids, but they're iron oxide framboids. They're beautiful. And you can see they look the same. It's a pseudomorph of iron oxide after iron sulfide, basically. Okay, so here's that reaction front. It's very narrow. So that's telling you that the reaction was fast compared to the water flowing through the system. It happens right above the water table, and this is where the water table is varying. You can see it right here. Okay, so we wrote a whole paper about this. Jingu co-author or first authored it. It's in Science, and we kind of do a deep dive on putting this same kind of picture together for pyrite. And this latest work that Liao has promoted is now where we're trying to do the same thing for chlorite. And we haven't gone as far as we have with the pyrite, and I don't understand it as well. So I have a lot of courage giving it to the Clay Mineral Society, where you guys understand clays more than I do. Okay, so this particular rock is mostly quartzanilite and about 14% chlorite. And something like 80 or 90% of sedimentary rocks have chloride in them. And the norm is something like 15 to maybe at most 30% chloride. So chlorite's an important mineral. It's a complex mineral, and it's very reactive. And that's why I think it's important, and that's why we ended up studying it. So I don't know if you can see this because of the lighting here. The green is illite, the blue is quartz, and then the sort of pink and orange colors are the chlorite, present at about 14%. And then you can see some backscattered images where you can sort of see the sort of scale of the porosity and that sort of thing. The chlorite in this rock is iron rich. There's a lot of iron, and this was part of the Clinton Formation, which is an ironstone formation, which was actually mined in the early years and used for iron to build a railroad across the US, because Pennsylvania was the center of, the start of that. But it's basically a shamosite chlorite. Okay, so the first thing that we think happens to the shamosite is kind of like that pyrite. The first thing we think happens is the iron starts to oxidize. And we've done a lot of titrations on, when I say we, I really mean Rusha, Liao, and Jingu, did titrations on them, but we also, in order to look more precisely at sort of grain by grain, they use this electron probe microanalysis technique that looks at the L spectra for iron, and the ratio between the L beta and the L alpha intensity has been shown to tell you about the percent of Fe2 of total iron in your system. And so that's what's plotted here. And it's plotted versus the content, the magnesium content of the chloride. And basically what I want you to see, although there is some variation in the magnesium content, the iron is oxidizing without loss, so without changing the magnesium content. So we argue that the first reaction of the chloride is this oxidation. Okay. So the first thing that happens, we think, in the chloride is oxidation. And then as you come upward, a whole series of reactions occur. And as clay mineralogists, you probably know something about this. So these are X-ray diffraction as a function of depth. And the depths are over here, helpfully done in feet because that's how drillers do them. So from bedrock to sap rock. Sap rock is the word I use for weathered rock that hasn't disaggregated, and then soil up here at the very top. And the XRD patterns, first of all, the illite peak here doesn't change very much. Illite does start to weather, but only in the very, very top. So it's the least reactive of the clays. On the other hand, the chlorite starts to weather, and you can see these are the two chlorite peaks that are most diagnostic. And you can see the change as you come to the surface as it changes from bedrock to sap rock to soil. So we did many of the heating and saturation, cation saturation experiments to see what's going on. And I just put these in here because I thought some people out here maybe really enjoy looking at these wonderful kinds of plots. Here we've done the very deepest. This is the bedrock or protolith. And again, if you ignore the 10 angstrom peak, which is mostly the illite, you can see that in the bedrock, no matter what you're doing to it, you're seeing very little change to the 7 angstrom peak and the 14 angstrom peak. However, you get up into the sap rock, you start to see a little tiny bit of change when you potassium saturate and heat it to 550. And then higher in the sap rock, you're starting to get evidence for hydroxy interlayered vermiculite, and you start to see much bigger changes in that 14 angstrom peak, until finally up here, you're losing evidence of chlorite, and you're seeing the HIV and the vermiculite only. So Rucher and Jin used Crystal Maker and data from electron microprobe and EDS, and then structural data from the literature to make a model for how this chlorite is weathering. So chlorite is a 2-1-1 clay. So the TOT layer and then the hydroxy interlayer. And they used all the chemical information they could to constrain this model. And this is the sort of picture of the bedrock chlorite. And then the first thing, as I said, is oxidation. So you start to see some of these, I think the blue is the iron 2 oxidizing, and that's turning black here. And then the next reaction is to start to lose some of this hydroxy interlayer. And that's when you start making your hydroxy interlayer vermiculite. And then finally, when this is all lost and there's just some magnesium and water in the interlayer, you get to vermiculite. So with this crystal model that fit all the data that we could constrain, they then made the X-ray diffraction, which I think some of you took a short course on how to do this. This was done with Crystal Diffract, and Peter Heaney was involved in this as well. And you can see then, this is the diffractograms that they calculated, again, for the bedrock, for partially oxidized bedrock. This is just for the chlorite, then the HIV and the vermiculite. And again, if you look at the 7 angstrom and 14 angstrom peaks, and the ratio of those two peaks, those change not with oxidation, but when you go all the way to the vermiculite. And so they also calculated that the ratio of the 002 reflection to that of the peak intensity of the 001 reflection is called the CV. And the CV for the starting chlorite was 4.4, and it decreases like this as you go from chlorite to sap rock with the chlorite plus the HIV to the hydroxy interlayer vermiculite plus vermiculite. And so this CV was a way that we could use when we look at profiles now to show that vermiculitization that's happening. Okay, so now let's go and look at the data. And again, let's go to this north farthest up the watershed borehole. And these are tau plots, and you're an expert on these now. This is the sulfur tau plot showing you in that borehole where the pyrite oxidatively dissolved, way down here. Then this is showing you that right there is also where we start losing iron 2. So this is where oxidation of the iron 2 in the chlorite and in the rock happens. And so oxidation happens very deep. And then we end up with some iron 2 coming all the way to the surface because there's some iron 2 in the illite as well. Here is the loss of magnesium. I said the oxidation happens earliest. So loss of magnesium is where the really the inner layers start dissolving. And so that happens only after iron oxidation, and it's a very slow reaction. So this is a very fast reaction, narrow front, very slow reaction, very wide front. And then here's that CV versus depth, really fast change at first and then slow change, but that's related to what oops, I'm going the wrong way. That's related to what I showed you here, namely, it changes very fast and then it changes slowly. And then this is just emphasizing that all of this starts just above the water table. Okay, so that was that borehole on the ridge, but far from the outlet. Now let's go to the ridge, but closer to the outlet. And that's here. And first of all, the oxidation starts shallower. We still see, this is the pyrite front. This is much more complicated, but you still see most of the sulfide in the pyrite is lost at a shallower depth. But now all of a sudden there's two fracture sets at depth where some oxidation occurs. And so most of the pyrite oxidation happens at this front right here, but there are some deep fracture sets where water is getting down with oxygen. And so, we'd like this front, this landscape, if you will, to be like a planar kind of smooth surface, but it's not, because these fractures mean that it's actually not just a sort of smooth surface. Here's oxidation of iron happening again. We see it in these fracture sets. These sort of brownish things are the fracture sets. Here's that slow loss of magnesium upward. Here's the vermiculitization happening. And you can see that as well. And again, this is all happening just above the water table. Why is the front higher here? It's because the water table is not as deep as you go towards the outlet. Okay, now let's look at a valley borehole here. And here are the plots for the valley. And this is the plot I just showed you from that south ridge. Here's the loss of pyrite. Again, it plots here with some variability, right? These are rocks. Here's the pyrite in the parent material. Here's that oxidation front for the pyrite, and then all the pyrite's gone. So you see two things. First of all, again, the reaction starts pretty deep, but the reaction front itself is now very, very wide. And in this case, the chloride oxidation doesn't start really until almost all the pyrite is gone. And the loss of magnesium doesn't start till most of the pyrite is gone. And the vermiculitization doesn't start until the pyrite is gone. So it's kind of a puzzle, why the valley is so different than the ridges. But remember, the ridges, I keep talking to you as if they're 1D. If you get to the valley, of course, that is nothing's 1D, but the valley is really not 1D. And so the way we think about this, at least to first order, is here's our watershed. These are the ridge lines up here. This is where water is basically going in. So that's a recharge area. I emphasize it's 1D. The water is going in and going down and out of the system. Down here, the way a watershed works is like a bowl. So the water, is funneling, actually at the surface funneling towards the outlet, but even in the subsurface, it's also funneling towards the outlet. So that's where, water has gone in along the ridges and then it's coming up along the outlet. So this is, lots more water is going through the subsurface, But then also, although some of the water is going out under the outlet, some of it's actually coming up. So that's actually, and there's an upward spike of water as well. So let's try to think about the water flow to kind of just put this in perspective. This is a critical zone observatory. We had lots of different people working there, geophysicists, hydrologists. So we know a lot about the water flow. We know it's about 1 meter per year rainfall that comes in. And I should explain this plot. It's a tau plot, but it's a little bit different than what I've showed you. This is depth. And, this is parent composition, 100% gone. Here's the pyrite front, very narrow, very deep. I didn't mention, but there's a tiny bit of carbonate, and that's very common in shales. The carbonate usually dissolves away right where the pyrite goes, probably partly because the pyrite produces sulfuric acid. Here's that chlorite front, very wide. And then this is where the illite dissolves away, right at the surface where the rock disaggregates. Water comes in 1 meter per year, about half of that evaporates. And then we know from the hydrologists that most of that leaves the system very shallow. So most of it flows out in this upper, say 5 or 8 meters, which is a very fractured layer. And so that is where it's highly fractured and the rock disaggregates to soil. But we know that some of it goes down to the regional water table because that's the water that's flowing through the chlorite front and weathering away the chlorite. And then some of it leaves at the regional water table. So if you look at this in 2D, it looks like this, where it comes in, most of the water is moving out that fractured zone. And that's the zone where the illite dissolves. A little bit of it comes down to where we have the carbonate reaction front and the pyrite reaction front. And then some of that water flows out the system. And so that water is all focusing under the outlet. And so this reaction front that I showed you, you can't think of it the way I taught you in the very beginning, which was a 1D model, because it's actually a front that's dictated by water flow that's lateral as opposed to vertical. So, but when you look at this, I think it kind of is striking that these reaction fronts are located right where water flows change direction. So this is the illite front up here, water's coming in and then it's mostly going out. And then the chlorite is a wide front, so it's showing you water's going through it. So every one of these narrow reaction fronts, it's a place where there is a change in porosity and permeability and a change in water flow. So I like to think of these fronts as either causing water flow change, direction change like a valve, or at least manifesting where water flow changes in direction. And you can model things like this. This is, again, just quartz plus albite going to kaolinite plus quartz. And we started with a homogeneous hill and allowed water to flow in. You can see the flow lines in white here. The color, the red means all the albite has dissolved away. The blue means you still have the parent composition. Here's the reaction front, modeled reaction front, this yellow. And basically, as the weathering occurred in the model and albite was dissolving, kaolinite precipitating, that created porosity, which changed the flow lines. And so we're trying to argue here that if you have porosity and permeability updating in your model, it actually can control where the water flow lines go. So that's where this idea comes from, that the reaction front is kind of like a valve in the system. Okay, now this is how Rusha drew it in her paper to show you. I don't know if this is helpful or not, but this is down at the valley. Here's that, water coming in 1D at the ridge. Once it gets through that zone that has xylite and hits the sap rock where you start to see chlorite, a lot of the water just flows laterally, but some of it makes it all the way down to the regional water table. And then it moves like this. And by the time it's flowing through that reaction front under the outlet, it has lower oxygen, because we've measured it, than under the ridge. There's more water flowing through under the outlet, and it has a higher pH. So all of those reasons are probably explaining this very wide reaction front under here. So, there should be a picture in your head. You've got the landscape, and underneath it, there are these landscapes that kind of mimic the surface, but they're kind of, coming up to the surface under the outlet and opening up into almost like like a trombone shape or something, because it's a wider kind of front at the subsurface. Okay, well, wouldn't it be nice if we could map this? Because I'm kind of just making arguments based on points, 1D cores. And these are the same data I've showed you before for one of the boreholes, but now I've put porosity on here. So here's porosity of the parent rock, and then where the chloride starts dissolving. You can see this is where the chloride's dissolving because you're losing some magnesium. Your porosity goes up. And so we noticed that wherever the chloride was reacting, that's where the porosity was increasing in this particular rock. And porosity in the subsurface is something you can measure geophysically. And so we thought we would work with geophysicists to try to map out these reaction fronts in the subsurface, or at least try. So this is data from a 2D refraction seismic transect, so across the watershed. And we went through one of the boreholes I talked about and the other borehole I talked about, because that's where we can take our samples and know theoretically everything we want to about those samples as a function of depth. And this was done with Andy Nyblade, who happens to be my husband, and his grad students, who are the first authors on some of these talks. So seismic velocity, I'm not going to talk about all the modeling and the parts of it that is not what I do, but my husband does and the students did. But the seismic velocity, so how fast a seismic wave moves through a rock, is a function of many things, but one of those is the porosity of that rock. And so here now is a map of the seismic velocities that I'm going to turn into a map of porosity in a minute. So this is elevation and distance from this borehole that I showed you a lot of data for in this borehole. This is where pyrite oxidation starts, and then this is where it starts here. This is that thin reaction front, and then the reaction front for pyrite is very wide here down at the valley. And this is where chlorite dissolution starts, and this is where chlorite dissolution starts. And the upside down triangles show you where the water tables are. So chloride dissolution starts under the valley. What we noticed, this is where it starts, where that brown hatched line is, it starts at about 2,700 meters per second. That's the seismic velocity at that point. And up here, the chlorite weathering dissolution starts at 2,700 meters per second. And so our hypothesis was that is showing you a map of that, the bottom of that chlorite reaction front. And so what geophysicists can do is take a rock model, which can actually calculate what the seismic velocity should be for any, set of, lithology, mineral content, porosity of a rock. And then we should be able to, use our rock model at the boreholes where we know what minerals are present, what the porosity are as a function of depth, calibrate it, and then extend it. And so this shows you that rock model. I can't really explain this in the short amount of time that I have. This is work done with Gary Mavko, but basically it's saying that the ratio of the P wave velocity to the S wave velocity plotted versus the P wave velocity for this particular rock with the composition that we know with the different minerals, if all the pores are water filled, it should plot along this line. If all the pores are gas filled, it should plot along this line. And here are the data points. We got the VP to VS and the VP from downhole sonic logging in each of the boreholes. And so this is for one of the boreholes, and it's color coded for depth. So basically, the rock has a porosity of about, 2.5%. And at the deepest depths, so the dark colors, it's water filled. And then as you go to shallower, it starts to become partly gas filled, which was kind of a discovery because we would have thought this was all beneath the water table. We would have thought there wouldn't be any gas filled. But at any rate, we now can go from seismic velocity to porosity. And so up here is the seismic velocity cross section, so measured and then modeled. And now this is the porosity calculated from the rock physics model. And it basically matches everything we know about the rock at these boreholes from all the different measurements that we can. So you can see now that we are mapping out this porosity. This is the landscape, of the weathering beneath the surface. Oh, and the only other thing I was going to say is some people would say seismic velocity isn't really showing you porosity, it's showing you fracture distribution. But we made an argument that the fracture, these are the density of fractures as a function of depth in these two boreholes. And they're so different in the two places, and especially where this chlorite weathering starts, that a simpler explanation for the seismic velocities is the porosity created by the chlorite weathering and not the fracturing. So this is what, it really looks like. You have oxygen-rich water here. Some water makes it down to the pyrite reaction front, and it starts with some oxygen, and as it moves to the valley, it's more and more depleted. And then we have measurements down here that shows this is where upwelling starts to occur, and this is where water keeps moving down and out of the system, and that's right at the pyrite oxidation front. So again, these reaction fronts seem to locate at places where we're seeing changes in the water flow. And so that's why I like to call them valves. They may not be causing it. The water flow could be causing where the reaction fronts are, but certainly the two things are connected. Okay, so this is one place. Why would you think this is even important? Well, we looked at some of these patterns in two other shales, one in Northern California and the other in Taiwan. Taiwan is the fastest eroding shales probably in the world, or some of them. And, we saw a lot of the same things, and I'm really ending here, so I can't go through this, but we saw unweathered pyrite, and in Pennsylvania, weathered pyrite was iron oxide. And we saw that in California, pyrite framboids, iron oxide framboids. We saw it in Taiwan, pyrite framboids, iron oxide framboids. This is when the erosion rate increases 100-fold. And here are the tau plots. So I've already gone over this one quite a bit. What I really want you to focus on, the pyrite fronts are always really narrow. Pyrite oxidation is really fast compared to any of the transport processes. Chlorite reaction was slow, as I've been emphasizing, but as the erosion rate goes up, all of a sudden you start to see some chlorite that's actually emerging at the land surface. And this is what I told you way back in the beginning, the chemical depletion fraction is you expect, for a very slow erosion rate, you can get a very thin reaction front, but as your erosion rate goes up, you're going to eventually expose your reacting mineral. And that's exactly what you see in these chlorite fronts. So this just shows you, I think, a little bit that what we're talking about is happening all around the world. We just need to be able to understand it better and kind of unravel it. So that's it. That's my talk. I tried to show you that the delivery of oxygenated water to the subsurface appears to initiate the weathering of shale. I think in many cases and in many rock types, that oxygen gets down there and creates some of the first reactions that really starts the weathering and starts forming these landscapes in the subsurface. I showed you that there's a reaction front for oxidation, a reaction front for dissolution, and that kind of mimics the surface of the land. But, as you go towards the outlet of your watershed, it becomes more complex. And I showed you geophysics can map these, the sort of the geomorphology, if you will, of these reaction fronts. And then I showed you that the reaction fronts may act like valves, or they may just sort of manifest valves where the water flow changes. So I hope you have a little appreciation for the clay reactions beneath your feet. So thank you very much.
Okay, and we'll address questions right now. Hold on one second. Let me check one thing. First off, good, it was not on mute. There was a concern at a moment. I'm going to check the chat real quick. There is nothing in chat. Okay, cool. We'll go ahead and answer questions in the room.
Am I choosing my people, my questions? Oh, I see. Yep. Okay.
Thank you, Sue. Mike Whitaker from Berkeley Lab. So earlier on in your talk, you had a bullet point about oxygenated and carbonated water. And here in the conclusion side, you mostly focus on the oxygenated part. Is there a CO2 story also playing out in your CZO and some of these other systems that you didn't have time to talk about?
Oh yeah, absolutely. I mean, I think of weathering as redox, oxidation reduction, and then acid base. That in a nutshell, that's what weathering is. And so, oxygen is maybe the most important oxidant, and then CO2 is probably the most important of the acid bases. And so, yeah, I mean, anytime the base metal cations are moving out, that's typically an acid-base mediated reaction. And we did measure CO2 gas in various places around the watershed. We did a little bit of modeling of that, but we didn't figure everything out.
Thank you.
Prakash has a question in the back.
Thank you so much, Susan, for a great presentation. And I'm not that old, but it brings back the memory from 35, 40 years ago, looking at those soil profiles. And also, I need to talk to Michael Cesar here. How did it happen? That's two. One, alumnus from Penn State yesterday, and today professor from Penn State.
We are.
Okay.
The joke. The answer.
Joking aside, could you shed some light on what I understood is the chloride transforming to hydroxy-aluminum interlayer vermiculite, then vermiculite. Is that the sequence you are talking about? And also what kind of water chemistry, because you need to dissolve aluminum, at low pH to form the aluminum hydroxide interlayer, right, in the vermiculite. So what kind of chemistry going on from the water chemistry point of view? And if you confirm the sequence of weathering from chloride to vermiculite via hydroxy-aluminum, hydroxy interlayer vermiculite?
So some of the aluminum is precipitating as kaolinite. So I didn't really talk about formation of kaolinite, but there is some kaolinite that eventually forms. So that's where some of the aluminum goes. Some of where this, if you can move aluminum at all, it has to be because of acid-base reactions, or you have to have organic ligands down there. I'm talking pretty deep, and we normally think that the organic ligands get consumed higher up in the soil. But so some of it has to be water that is acid enough to move the aluminum, and then you have to have a long enough time period to be able to move it in the very small amounts that can move. Does that address your question?
Yes, in the soil, most of the hydroxy interlayer vermiculite is dioctahedral, right? Here is a chloride, most likely is trioctahedral. And most of the soil on the surface of subsurface, both vermiculite and the hydroxy interlayer vermiculites, I think they are dioctahedral. So I guess there is a additional.
Yeah, I'm trying to move the slides, but it doesn't seem to be moving anymore. I don't know if there's a trick. There we go. I'm trying to go all the way back to the, I guess I could do this in a less clicky way, but oh, there we go. So so some of the aluminum is up here in the TOT layers, and some of it's down here. So we're not getting rid of all of the aluminum, but we are getting some of it could be being removed. But we are producing some kaolinite as well.
Thank you, Susan. On a personal note, I did work at Penn State at MRL for 5 years.
We are.
Thank you so much.
You mentioned that you did some downhole logging. You did sonic and NMR. Do you get a chance to run spectroscopy logs? And if so, are you seeing that same chemical signature in the spectroscopy logs?
We didn't do spectroscopy logs. We're not as maybe fancy as that or whatever. I thought we ran almost all the logs that we could, but I mean, to me, I don't know why I went through my whole career without realizing that geophysics ultimately becomes geochemistry when you get to this level, you know, but to me, it was just a marvel that you could do this. I mean, now I've started thinking about, you know, geochemistry, what makes it geochemistry versus geophysics? Like what's the difference really when it really, you know, it's all the same. Like geochemistry is, you know, sample by sample. We can analyze everything in the sample. The geophysics, you know, allows you to look over the 2D and the 3D. And so we really need to work more with the geophysicists, like I think some of the oil companies do.
Great, Sue, thanks. So now you've just informed me life is just nothing but pushing protons and electrons, right? But speaking of life, I know you just didn't have time to address it, but you know, there's a lot of geomicrobiology going on here. Can you tell us what your groups are doing in terms of understanding what the microbial populations are doing to drive this process?
Yeah, so I'm doing pretty well remembering all my clickers here. We spent a lot of time thinking about that with the pyrite. Where's my picture of the pyrite? As soon as you have pyrite oxidation, of course, everybody thinks of microbes. So the paper that we wrote is deep abiotic weathering of pyrite. And the argument went like this. First of all, everyone assumes if you have pyrite oxidation, it's microbially oxidized. So we thought that's probably what would happen. We did hang little collector, like tea bags of pyrite down in our boreholes and then took them back into the lab. We worked with Eric Roden and Stephanie Neporalski, and she published a paper. There are iron oxidizers and sulfur oxidizers in the watershed, no surprise. But when we looked at the samples here, the shale down here, there's a very small amount of pyrite. When pyrite oxidizes, it produces sulfuric acid, so it'll dissolve a little bit of carbonate. But we're not talking about a lot of dissolution. We're not talking about a lot of porosity development from the pyrite. And the rock is so tight, it has such tiny pores. We measured the pores with neutron scattering and other techniques. They're only about 2 to 10 nanometers. And the argument we made was that bacteria could not get into the pores where the pyrite oxidation is occurring. So we were actually able to get samples from our core where you can see a fracture and there'll be pyrite oxidation at the edge of the fracture. And then you go into the matrix, you see less and less pyrite oxidation away from that fracture. And so the oxidation is happening in the matrix where the pores are very, very tight. And so we made the argument that the microbes can't get in there. So I think it's interesting because this is really common, this pyrite oxidation at depth. In a tight rock like a shale or a lot of igneous or very tight metamorphic rocks, I don't think that oxidation starts biotically. I think it starts abiotically. The biota only get involved when the pores are large enough or the rock disaggregates enough that the microbes can get there. And yet, a lot of the pyrite is gone in this kind of a system, which is slow eroding, at depth. So I don't think that the microbes are involved with the pyrite oxidation. I don't think that the microbes are involved with the chloride oxidation at depth, only when it gets towards the surface and where the porosity starts to open up, do I think that those microbes can get in there. And I think that, abiotic people have given up too much space to the biotic. They don't get everywhere. They just don't get everywhere, I don't think. Yeah.
If I'm not mistaken, most area you have been studied is in Pennsylvania, also in Taiwan. There's plenty water supply and really, hot area. I'm just curious, we have a beautiful story here, but if you move to a colder, drier area, how does that going to affect, your observations?
That's a really good question. And that reminds me to say something which I was supposed to say, but I didn't. You know, when I talked about my perfect 1D system where I had a ridge with one lithology, I should have said precipitation has to be greater than evapotranspiration. So you have to have net water flow going down. I think it might have been on the slide, but I forgot to say it. So yeah, everything that I'm talking about is a system where there is a net water influx into the system. And large parts of the planet are so dry that that's just not always the case. So I think some of this, will happen, whenever there was water flowing through the system, you still can get weathering. If you have enough time, you can get these reaction fronts. And we do see reaction fronts in the western part of the US, for example, or in Australia. But there's other things that happen when the evaporation is high compared to precipitation. So for example, water starts moving back up and starts precipitating salts, and you start forming certain kinds of clays that hold a lot of these cations in place. So, in everything I've ever worked on, sodium, once it's dissolved out of a rock, it just moves out of the rock. It doesn't reprecipitate because there's hardly any mineral that'll reprecipitate with it. But in the western part of the US or in Australia or dry parts, sodium can sometimes be held in smectites at the surface sodium containing smectites that wouldn't necessarily form very often in the wetter parts of the planet. So about half the planet is very, very dry and doesn't really operate this way. This is the way one part of the planet operates or one part of the system operates. So it's a very good point.
And this is Yun Deng from Texas A&M University. I'm a soil mineralogist. I'm very curious about the weathering of chloride, particularly in the presence of pyrite. So when I learned soil mineralogy, I was told chloride is very unstable. Takes about 60 years to convert to some cells. Based on your experience, what's the fastest, shortest time chloride can fully convert to a vermiculite?
Okay, so I couldn't quite hear your question, but you're a soil scientist, you're interested in chloride, and you're kind of confused because it's so reactive. You're wondering why we're finding it here.
No, the question is how fast actually chloride will convert to vermiculite. And it takes tens of years or hundreds of years or thousands of years. So
Okay,
in a
so-
particular acidic condition.
Okay, now that I understand your question, I can't answer your question. I can tell you that that's like the next thing we want to do is be able to quantify the process. That's what we did in the science paper for the pyrite. So we quantified the rate of pyrite oxidation. And the rate of pyrite oxidation as it is recorded in these rocks is slower than the rate that you would measure in the laboratory. In fact, there's papers where people have measured it in the laboratory. And the reason it's slower in our system is that in the laboratory, you take a beaker and you put pyrite in and you mix it and you have oxygen coming in, so you keep it well stirred. In the rock, as I said, the oxygen has to get to where the pyrite is. So it has to either move down in groundwater, and then it has to typically diffuse from the fracture surface into the matrix where the pyrite still is. And that's also going to be true for the chlorite. So the reaction is slower than what you think it should be, because I think anyway, you're thinking about either a laboratory system or like a well-mixed soil where it's disaggregated and it's, seeing a lot of water and oxygen. And what I'm talking about is the rate of reaction of the chloride in a rock that has a very small porosity, very impermeable, very high tortuosity. And so you have to, diffuse your reactants in from the fracture surface, and that makes it very slow. And that, by the way, I can't remember if I said this or not, but I started out as a chemist measuring reaction rates in the laboratory, wondering why I couldn't predict them in the field. And part of the answer is that as you go to a bigger and bigger system, the things that you're really interested in your small system become unimportant, and new processes come in that can dictate the whole process that you're interested in. And, in particular, the erosion rate dictates the rate that these reactions happen. So how fast that rock is moving up and getting closer and closer to the surface really dictates how fast these processes happen. It's like the pacer. It's the pacer. And so I just think it's really important to think about, we can spend our whole career, measuring something that we think is really interesting and all our colleagues think is really interesting. And we think we're going to, solve water resources problems. And in reality, once we get out of that little system and move all the way up, we'll find something else was what's important. And so I think that probably addresses your question.
This has been Leg from P&L. That was a fantastic talk. I really enjoyed it. I think following up on your last statement, it made me wonder how much of these processes are continual steady state processes and how much might be dictated by like abnormal events, like maybe, I don't know, floods or earthquakes or whatever it might be. Do you have thoughts on that?
Yeah, that's a really good question. I think that's a really good question. I mean, I think as you look at a bigger and bigger system and look at a longer and longer time scale, even those get averaged out in the system. But it's very possible that, those fractures sets that I showed you for that one borehole, maybe those weren't open at one point. And once they opened, it really changed the system. So before that, sort of catastrophic event and after that catastrophic event, if that's what it was, the system would have operated very, very differently. So I mean, that's another piece of the puzzle that makes it very difficult to understand these systems over the long time frames.
Are there maybe, I was blown away by the amount of things you could learn by looking at a profile in terms of kinetics. And I'm wondering, are there signatures that you look for in there to look for those other sorts of deviations?
You mean like the more catastrophic events?
Yeah. Or
That's a really good question. You're asking somebody that, I look at it really from a continuum basis, and I've done that my whole career. So you're asking kind of the wrong person. I mean, because it's such a good question. And I mean, what do we do in science anyway? We look at something, we say, wow, that's a cool puzzle. And we say, do I only see it here? And if I only see it here, why is that? But what I like to do is find something that I see everywhere. And reaction fronts we see everywhere. And so that's a real thing. How much can we understand about them? And then I try to find places where I can understand them, and I kind of use a continuum model. But somebody else that's interested in those, fast catastrophic events is going to emphasize those in their career. And that's probably the best person to ask. I mean, certainly geomorphologists that look at landslides, in Taiwan, there's a lot of landslides and that sort of thing. You can't ignore them. I mean, you can't. So, each of us we're the blind person looking at a piece of the elephant in the best way we can.
So this discussion made me think of another question, and I just want to make sure I understand the model. So you made a nice molecular picture of how the chlorite is weathering through iron oxidation, and so you're losing that sort of interlayer and replacing it with water, presumably. Is that directly what leads to change in the geophysical sort of the change of velocity? Intermediates that like interlay, then something else happens to develop porosity, and then you measure that geophysically. Okay,
so you're pointing at this slide, which is the pyrite oxidation. There's such a small amount of pyrite in there, and the oxidative, reaction that happens. We thought we'd see that geophysically, but I don't think we did. It doesn't mean that you couldn't with some other tool, but I don't think we did. It's the chlorite weathering dissolution that creates the porosity, and that's what we think we see. So, and I think what you asked was, is there a secondary step or anything? And I don't think we need to argue for one. So, once the chlorite starts weathering, it is the most reactive clay in there. It's the most reactive mineral in there, except for the tiny amount of pyrite and carbonate, which there's such a small amount in there that we just don't think we see that geophysically. So once it starts dissolving and creating porosity, then we start to see it. At least that's our argument, because in this borehole, when we see chloride start to weather, that's right where we see it. The VP, the P wave velocity is 2,700 meters per second. And then we see it over here. So it's kind of a, existence proof, or I don't know if it's an existence proof, but, a correlation or whatever that we see. There's something else I was going to say in that. Oh, the only thing that correlates geophysically with the pyrite oxidation is in the valley floor. You know, if you think of all that water in the subsurface kind of going out underneath, you know, some of it is going out and down, some of it is going out and coming up. And I showed this in one of my last slides. There's a point, a depth where, you know, you can measure with a downhole flow meter, is the water got a vector going up or a vector going down, and right where they diverge is that's where we see that pyrite oxidation start. So I don't know why that is, but that is an observation that does correlate with the pyrite.
With the chloride, essentially, so you remove, it's less than a nanometer of stuff, right? Essentially replace that with water. And that's enough to change the seismic velocity.
Well, of course, you're not doing it with one clay particle, right? You have to, it has to be, you know,
Just,
right.
you know, for cheap whole projects that have like this solid.
Right. I mean, that's our argument. I mean, I could show you a plot. Well, I did show you a plot of porosity increasing upward. Now, you know, where does it have to have changed enough to see it? You know, the model, the geophysical model where I had that 2,700 meter per second, I mean, we can run that model in different ways. And it's, you know what I mean? It's not like a pinpoint, it's not a geochemical measurement, you know, it's geophysics, man. But yeah, that is the argument we're making, that you change the porosity. And, well, I'm not going to go back that far, but you know, that rock physics model that I showed, you know, the rock physics models, you put in the minerals, you put in the porosity, and then you put in, you know, whether you have gas or liquid in the pores, and then you can calculate the VP and the VS, and then, you know, that's all we did. So the answer is yes, but you have to have enough of it to be able to see.
Let's thank Sue again for a wonderful presentation.